Welcome student in Christchurch Convent Digital Classes, subject Chemistry, Class 12, Chapter 6, Part 2. So, in this video, we'll see about reduction of oxide to the metal. So, either by using a calcination process or roasting process, we obtained the metal oxide from its ore, and some other agent, a substance or reducing agent such as carbon or carbon monoxide or even another metal is used as a reducing agent. For example, carbon combines with oxygen of the metal oxide as shown in the chemical equation 6.13. MXOY means मेटल ऑक्साइड के नंबर ऑफ एटम x हैं और ऑक्सीजन के नंबर ऑफ एटम y हैं. They react with the number of atoms, y atoms of carbon, and give us x atom of metal and y moles of carbon monoxide. Some metal oxide get reduced easily while others are very difficult to be reduced. Reduction means electron gain or electronation. Gain of electron is also called electronation. In any case, heating is required to understand the variation in the temperature requirement for thermal reduction, pyrometallurgy, and to predict which element will suit as the reducing agent for a given metal oxide. Gibbs energy interpretations are made. Some basic concepts of thermodynamics help us understanding theory of metallurgical transformation. Gibbs energy is the most significant term here. The change in the Gibbs energy, that is delta G, for any process at any specified temperature T, capital T, is described by the equation delta G is equal to delta H minus T delta S, where delta G is the enthalpy change and delta S is the entropy change for the process. For any reaction, the change could also be explained through the equation delta G is equal to RT minus natural log K. Where K is the equilibrium constant of the reactant product system at the temperature T is negative. Delta G implies a positive K in the equation, and this can happen only when the reaction proceeds towards the product. From these facts, we can make the following conclusion. Before studying out the conclusion, we'll see one more line. During metallurgy, flux is added, which combines with gangue to form slag. Slag separates more easily from the ore than the gangue. This way of removal gangue becomes easier. Now, what are the conclusions? First conclusion is that when the value of delta G is negative in equation 6.14, only then the reaction will proceed further. The delta S is positive, means change in entropy is positive. On increasing the temperature, the value of T delta S would also increase. That means delta H will be less than T delta S, and then the delta G will be negative. If the reactant and products of two reactions are put together in a system and the net delta G of the two possible reaction is negative, the overall reaction will occur. So the process of interpretation involves coupling of the two reactions, getting the sum of their delta G and looking for its magnitude and sign. Such coupling is easily understood through Gibbs energy versus T, means the absolute temperature plots the formation of the oxide. You can see the figure 6.4. These are also called Ellingham diagram. The graphical representation of the Gibbs energy was first used by H. J. T. Ellingham. This provides a sound basis for considering the choice of reducing agent in the reduction of oxide. This is known as Ellingham diagram. This is also important. In one time it is asked describe our Ellingham diagram. Such diagram help us in predicting the feasibility of the thermal reduction of an ore. The criteria of feasibility is that at any given temperature the Gibbs energy of the reaction must be negative. Ellingham diagram normally consists of plot between delta G versus T absolute temperature, the formation of oxide of the element, that is for the reaction. So 2 mole of 2xm solid plus O2 will get 2mxO. In this reaction the gaseous amount is decreasing from left to right due to consumption of gases, leading to a negative value of delta S, which changes the sign of the second term in equation 6.14. Subsequently, delta G shifts towards higher side despite rising T. Normally, delta G decreases, that is, goes to the lower side with increasing temperature. The result is positive slope in the curve for most of the reaction shown above for formation of metal oxide MXO solid. B. Each plot is a straight line except when some change in phase solid to liquid or liquid to gas takes place. The temperature at which such changes occurs is indicated by an increase in the slope on the positive side. For example, in case of zinc and zinc oxide, the melting is indicated by an abrupt change in the curve. There is a point in curve below which delta G is negative, so MXO is stable above this point. MXO will decompose on its own. In Ellingham diagram, in Ellingham diagram, C point, there is a point in a curve below which delta G is negative. Above this point, MXO will decompose on its own. D. In an Ellingham diagram, the plot of delta G for oxidation and therefore reduction of corresponding species of common metal and some reducing agent are given. The value of delta G etc for the formation of oxide at different temperature are depicted, which make interpretation easy. And E point, similar diagrams are also constructed for sulfides and halides, and it becomes clear why reduction of metal sulfide is difficult. Therefore, delta G and the delta G of metal sulfide is not compensated. Now, limitation of Ellingham diagram. The graph simply indicates whether a reaction is possible or not, that is, the tendency of reduction with a reducing agent is indicated. This is so because it is based only on the thermodynamic concept. It does not say about the kinetic of the reduction process. That is, cannot answer the question like how fast it could be. And the interpretation of delta G is based on K, which is the equilibrium constant of the reactant side. Delta G is equal to minus RT ln K. Thus, it is presumed that the reactant and products are in equilibrium. So, metal oxide, when react with a reducing agent, X mole of metal and reducing agent का oxide मिल जाता है. This is not always true because the reactant product may be solid. However, it explains how the reactions are sluggish when every species is in solid state and smooth when the ore melts down. It It is interesting to note that here delta H enthalpy change and the delta S entropy change values for any chemical reaction remain nearly constant even on varying temperature. So the only dominant variable, equation 6.14, become T temperature. However, the delta S depend on much on the physical state of the compound. Since entropy depends on disorder or the randomness in the system, it will increase if a compound melts, that is from solid to liquid, or vaporizes from liquid to gas. Since molecular randomness increases or changing the phase from solid to liquid or from liquid to gas. Now, application of Ellingham diagram. Extraction of iron from its oxide. You can see in the equation 6.24, iron oxide FeO, which is in solid state, when react with carbon solid or coke, it convert into iron solid or liquid, and carbon monoxide is released as a gas. For example, in blast furnace, this process is used in blast furnace. Here you can see the Ellingham diagram for different metals and their oxide, formation of their oxide, and it indicates the stability of their oxide also, and suitable reducing agent for the reaction also. Blast furnace is important. One year it is asked, describe the extraction of iron metal through blast furnace and write the equation of different zones. So this is important. We'll see how iron is extracted from the blast furnace. So you can see the diagram of blast furnace. There is a cup and cone arrangement from which ore and limestone and coke is dropped, and there is a different temperature zone: 1070 Kelvin, 1270 Kelvin, 1570 Kelvin, and 2170 Kelvin. So on the upper side with purple color you will get molten slag, and with golden brown color you will get molten iron, which is also called pig iron when it is cooled. And molten slag is removed as a solid waste, and a different reaction taking place. Exhaust gases like carbon monoxide and CO2 escape out, and iron ore when react with carbon monoxide it forms hematite, iron Fe3O4 iron ore. Then when Fe3O4 is react with CO, it will form FeO, and CO2 is escaped as a gas. We are using limestone calcium carbonate. When it heated, it is converted into calcium oxide, and calcium oxide when react with SiO2 silica oxide, it will form calcium silicate, which act as a slag, and when it become molten state and easily removed, skimmed off. You can see in the equation. Then iron oxide when further react with carbon monoxide form iron, and CO2 is removed as a gas, and coke is reacted with CO2 and form 2CO monoxide, which act as a fuel gas. So in the final step, iron oxide when react with carbon or coke, it will give molten iron, and carbon monoxide is removed as a gas. So these are the reactions taking place in the blast furnace. So in the blast furnace, the reduction of iron oxide take place in different temperature ranges. Hot air blown from the bottom of the furnace and coke is burned to give temperature up to 2200 Kelvin. In the lower portion itself, the burning of coke therefore supplies the most of the heat required in the process. The carbon monoxide and heat moves the upper part of the furnace In upper part, the temperature is lower and the iron oxide Fe2O3 and FeO4 coming from the top are reduced in steps to give iron oxide FeO. Thus, the reduction reaction take place in the lower temperature ranges and the higher temperature ranges depend on the points of the corresponding intersection in the delta G versus T plot as shown in the Ellingham diagram. These reactions can be assumed as follows. At 500 to 800 Kelvin, which is called lower temperature range in the blast furnace, the reaction mentioned in equation 6.28, 6.29, 6.30 take place, and at 900 to 1500 Kelvin at higher temperature range in the blast furnace, carbon react with carbon monoxide to give carbon dioxide, and further when iron oxide react with carbon monoxide, it will give iron and carbon dioxide. Limestone is also decomposed to calcium oxide, which removes silicate impurity of the ore as slag. Slag is in molten state and separate out from the iron as a solid waste because it becomes solid when it cool down. The iron obtained from the blast furnace contain about 4% of carbon and many impurities in smaller amount, for example sulfur, phosphorus, silicon, manganese. This is known as pig iron and cast into variety of shape. Cast iron is different from pig iron and is made by melting pig iron with scrap iron and the coke using hot air blast. It has slightly lower carbon content and is extremely hard and brittle. Further resection, wrought iron or malleable iron is the purest form of the commercial iron and is prepared from cast iron and by oxidizing impurities in a reverberatory furnace lined with hematite. This hematite oxidizes carbon to carbon monoxide and it will give you pure iron. Limestone is added as a flux and sulfur. Silicon and phosphorus are oxidized and passed into slag. The metal is removed and freed from the slag by passing through rollers. Similarly, copper can be obtained extraction of copper from copper oxide or copper 1 oxide, that is copper pyrite. Cu2S is called copper pyrite. We'll see this in the next video. Thank you for watching. See you in the next video.